Hello and welcome to another digital design class. In the previous class, we spoke about the analysis of clocked sequence circuits, and we solved some practice problems using the graph for analyzing clock sequence circuits. Today, we will continue with that, and we will continue with the Mealy and Moore models and how we can utilize these analysis systems to be able to simplify a sequential logic circuit. So as you remember, for a combinational circuit, we use different techniques such as K-map or Boolean algebra to simplify those functions. For sequential analysis, we use systems such as the Mealy and Moore models. So the Mealy model, the outputs are function of both the present state and inputs, and which is shown in the next graph. The outputs may change if the inputs change during the clock pulse period. The outputs may have memory, may have momentarily false values because they have memory again, unless the inputs are synchronized with the clocks. The Moore model, the outputs are function of the present state only. So the difference between the Mealy and the Moore model is that the Mealy is a function of both the present state and the input, but the Moore model is a function of the present state only. The outputs are synchronous with the clock in a Moore model, but in Mealy it can be synchronous or it may not be synchronous. This figure shows the Mealy and Moore models, the structure for them. The upper one is the Mealy machine. We can see we have the input, which gives a feed forward to the output combinational logic circuit. We have the next state combinational logic. We have the state register, which has its own clocks. And the output is connected to the output combinational logic. And we have a feedback coming back. And this creates a sequential logic circuit because of the feedback. And for a Moore machine, we don't have this feed forward that we had in the Mealy machine. The input goes to the combinational logic, and then to the state register, and finally to the output combinational logic. And we have the feedback here, same as this, which creates a sequential logic circuit. So the only difference between the Mealy and the Moore is the Mealy has this feed forward, which goes directly to the output combinational logic. The Mealy doesn't have. Mealy machine doesn't have. Moore machine doesn't have that, but the Mealy machine has this feed forward. Now, these two tables shows the Mealy and Moore models and the difference between them. For the same state between the Mealy and Moore, the output changes with the input for the Mealy, but for the same state, the output does not change with the input for the Moore. And you can see here, this is an example. The present state here is 0, 1, 0, 1, and 0, 1, 0, 1. Here we can see the output has changed with this same input, but here the output would not change with the same input. So again, we have the same inputs and the present state, and the output does not change. But in the Mealy model, because of the synchronous issue, it may change with the input. Now, the Moore state diagram looks like this. We have the state and we have the outputs. By the way, I have to update your PowerPoints on the website as well, because in that one I haven't added the registers, but here I added the registers and counters as well. So for a Moore state diagram, on the left we have the state, and on the right side we have the outputs. So for example, here the state is 0, 0. This is from the same table that we had before. the output is 0. And for going from 0, 0 to 0, I have 0. So 0, 0 to 0, I would have 0. And so on. So 0, 0 to 0, 1, I go with the state of 1, and then 0, 1 to 0, 1 could go with 0, and so on. We have solved an exact same problem with this. Now that we learn about flip-flops and sequential logic gates, we want to learn about the next more advanced type of sequential logic gates, or the sequential logic circuits, which is called the registers and the counters. Let's step back for a minute to remember that the most basic system, logic gate system that we had was AND, OR, XOR, and NOT. These are our basic gates, combinational logic circuits. And we can add them together to build a combinational logic circuit. An example of a combinational logic circuit is a full adder, half adder, decoder, encoder, multiplexer. All of these are combinational logic circuits. Why? Because they don't have memory, and the output is only dependent on the input at that time, okay? Then adding a feedback to a combinational logic circuit, we create a sequential circuit. What is the difference between a sequential and a combinational? The difference is that a sequential circuit has memory because of the feedback. The sequential circuit sometimes has a clock, and the output is depending on the input at that time and the previous state of that gate. Some example of sequential logic circuits, the latches, flip-flops, different type of flip-flops that we had, JK, D, and so on. Now, so using gates, we can build combinational logic circuits, and using those gates, we can build sequential logic circuits. Now, by using sequential logic circuits, such as flip-flops, we can build registers and counters. By the way, flip-flop is the simplest form of memory. If you want to save 1 bit, the simplest form that we can do that is using a JK flip-flop, okay? Registers and counters are also made out of memories, and I'll explain more about this. So what is a register? Registers and counters are clocked sequential circuits. A register is a group of flip-flops, so it's made out of flip-flops. Each flip-flop is capable of storing 1 bit of information. As mentioned, a flip-flop can store 1 bit of information. An n-bit register consists of n flip-flops. It is capable of storing n bits of information. Besides flip-flops, a register usually contains combinational logic to perform some simple tasks. In summary, flip-flops to hold information, and combinational logic to control the state's transition. So a register is a combination of a sequential logic circuit and a combinational. It has both. Now, what is a counter? A counter is essentially a register that goes through a predetermined sequence of states. Okay. Why do we need to have a memory in a counter? Okay. If we don't have a memory, we can't count anything. When we are counting 1, 2, 3, 4, we already know that the previous number was 3. Then we add 1 to it when we get 4. Then we save 4, we add 1 to it, we get to 5. If we don't have memory, each time we add, we go back to 0. So we're going to have 0, 1, 0, 1, 0, because we can't store that 1 to be able to add 1 to it to come 2, and then. So the most basic part of any counter is going to be its memory, okay? If you don't have any memory, you don't have anything to add to on top of that. So usually a flip-flop with a combinational logic circuit, which is usually an adder, what you can do, you can have a full adder and add 1 to it, add 1, and then save it again in the same flip-flop. So imagine you have a full adder or a half adder. I'm just going to put like a full adder, which is combinational, and I add 1 to it. So for example, if this number is 0, 1, 1, 0, adding 1 to it, it's going to be 0, 1, 1, 1. And then I'm going to save it again in the same flip-flop. And again, adding 1 to it. So in each clock, I can add 1 to this. And each clock, I can add 1 to it. And I can count up. So we have, and I can subtract it again if I want, and have a countdown instead of having an increasing counter. Now, some applications of registers and counters. Registers are useful for storing and manipulating information. Internal registers in microprocessors to manipulate data, and counters are extensively used in control logic. For example, for a program counter in microprocessors. Okay. One example that I could say is for example, is for counting the number of inputs that you have. If you have a motion sensor and you want to count how many people are like going through, you can use a counter. That's a very simple example. Or counting from 0 to a certain number to measure distance or something like that. These are some applications. Now, this slide shows an example of a 4-bit register. And in this 4-bit register, it uses 4 D flip-flops. As you can see, all the reset buttons or reset pins are connected together, and it's connected to the clear, meaning we can clear this to 0. And all the clocks are connected together. Therefore, we have a synchronous system because all our clocks are connected to a central clock. And the data are D0, D1, and D2 going to the input and being stored as Q0, Q1, Q2, and Q3. Usually, these 4-bit registers are built in a single IC. We can have 4-bit, 8-bit registers. If we have an 8-bit, it means it could store 1 byte of data. 8-bit is 1 byte. Okay. So this is a 4-bit register. It can store 4-bit of data. So for example, if D0, D1, D2 is 1, 0, 1, 1, 1, or 0, 1, 1, 0, it could store this number. And as long as we power, by the way, this picture doesn't show the power. As long as we power these registers, it's going to keep the data. As soon as we set it, connect clear to 0, for example, this one is actually because it's a NOT, we have to connect it to a 1 or a 5 volts. Then it will clear all the outputs and everything becomes 0. So that is a reset or a clear button. Or if we unplug it, everything is going to be erased. So as long as you have power, it's going to keep the data. And that's the reason why sometimes your computer or your phone doesn't work well and you reset it, even your washer, dryer, and all of that, because all of them have these microcontrollers, microprocessors. When you reset the system, you're resetting all these memories to 0 and it starts fresh from start. And usually, sometimes it solves that problem. Now, we can also modify this with some combinational circuit and create a register with parallel load, meaning that we can feed the data to them all at once. Again, this is a 4-bit register, so a little bit more complicated than the previous one. The other pin that we added was load, and load determines if we want to read or write on the system sometimes. So it helps with synchronizing the reading process or writing process in a register. Now, let's analyze this register with the parallel load. And by the way, if, for example, this load is 1, the output is going to be 0. Am I correct? And this output is going to be 1. So if this is 0, this would also be 0, the output of this. And this one would be 1. Now, depending on which input this is connected to, we can determine which input-output is connected and how they are connected and how the output and the input are related to each other. So for this, we have this graph. This is the loading register with a clock. The clock is shown with blue. The load is shown with black, and the input is shown with red. As long as the load is 0, the C input changes, and you can see here, and you can see that the clock is changing, but C input is not changing at all. Why? Because C input is connected here to the load. And without having any load signal coming in, we don't have any C input going in. And when we have the C input, the load, and the clock coming in, then we can transfer the data and store the data on the system. And I'll give you some examples of that. So this is an example of a register transfer. The blue, again, shows the clock. R1 shows the value of R1, the output, and R2 shows the value of R2. And the load for the second one is shown with black. So this is load for R2. Load for R2. And we can see here that, for example, when R1 is 1, R2 is 0, and it won't change. Okay, I'm going to draw it. Let me draw it with a different color, with green. So imagine if R1 is initially 1. At this point, R2 is 0, for example. And R2 will not change as long as load is 0. So as long as load is 0, R2 is not going to change. But at this point, load becomes 1. It means that R2 is now able to load data. But the problem is we don't have any clock because this is rising edge clock system. It's a flip-flop. So we are not able to change its output unless we have the next clock coming in. As soon as the next clock comes in, let me draw it with red, and we have load enabled, then R2 would change, status would change to 1. And the opposite is also true. If it was 0, then this would be 1 and then 0, for example. So the important point is that the output of R2 would not change unless the load is 1 and the clock allows it to operate and change status. This is a normal transfer register, R1 and R2. These are used for what we call shift register, and I will explain. We have left shift, right shift registers, and so on. And it's a serial register connected in series. And we also have other type of registers which can be connected in parallel as well. That one was in series. And for this one, this is another type of register transfer. We have R1 and R2. Here, the load of our load connects to the R1, controlling R1. And both of these are connected to an n-bit adder. So the outputs of register R1 and R2 are connected to an N bit. It could be a full adder. And the output is fed back to R1. And R2 and R1, again, are synchronized with the clock. This register is an adder, technically, and it adds R1 plus R2, and it puts it again in R1. So you can see we can have different combination of registers. Registers can also be used for controlling systems. This is an example of a data path and control unit. We have control inputs, we have the control unit, we have the control signals that connect to give actually order to the data path. And then we have the status signals, we have the control output, the data input, and the data outputs. Now, using this register, which was in series, we can create a type of register which is called shift register. So what is a shift register? As its name shows and indicates, a shift register shifts a binary code to the left or to the right. So a register capable of shifting its information in one or both directions. It's made out of few flip-flops in series or when we cascade them. The current state can be output in clock cycles. And in a computer, what a computer sees is, for example, if we have a 4-bit system and the outputs are 0, 1, 0, 1. So if the system is a register that shifts to the right, what happens is this 1 falls out, and if I shifted 1 bit to the right, then it will look like this. It will be 0, 1, 0, and the 1 fall out, okay? And we no longer have it. Now, what happens to the empty space on the left? Usually the computer replaces that with a 0. Okay. So 0, 1, 0, 1, you shifted 1 to the right. The 1 on the right is thrown out. And we have a 0 added at the end on the left. Another type of register is a shift left register, and it looks like this. Imagine I have, again, a 4-bit system. It's 0, 1, 1, 0, and I want to shift it 1 bit to the left. Can you tell me what it would look like if I shift everything 1 bit to the left? Each bit is going to be shifted 1 to the left. 1, 1, 1, 0. The last one, which is empty, we add another 0. And the 0 would fall out, okay? So this is shift left, okay? Or left shift resistor. We have another type of register as well that, imagine this is a 5-bit register. It's 1, 0, 1, 1, 0. This one is also shift to the left, but what it does, it has a closed loop. Whatever falls off from the right, from the beat at the most right, is replaced to the beat on the most left one, okay? So this one, if I want to shift 1 bit to the left, what happens? What would the answer be? This 0 would go, again, each would shift 1 to the left, and this 0 would shift back to. So I'm going to have 0, 1, 0. I'm sorry. Yes, 0, 1, 0, 1, 1. And I can do the opposite as well. We may have a system that has a shift, but it's to the left. But that one was to the right. This one is to the left. So again, this goes back here. Imagine this is a 4-bit system. if this is 1, 0, 1, 1, and I shift everything 1 bit to the left, then we would have 0, 1, 1, 1 as the answer. Now, let me give you an example. Imagine I have this digit 1, 0, 1, 1, 0, 1, 1, 0, 1, and I put it through a shift register that shifts to the right, and it's a closed loop shift register like this. What would the result be when I put it through this shift register? So everything shifts 1 to the left, to the right, I'm sorry. And this one goes all the way. So what I can do, I simply can erase the left on the right, the one on the right, and put it here. So it's going to be 1, 1, 0, 1, 1, 0, 1, 1, 0. Now let's continue with our shift registers. So in serial mode, a digital system is set to operate in serial mode when information is transferred and manipulated in 1 bit at a time. This is an example of a shift register in serial mode. We have the serial input and the serial output, and the serial output of register A is connected to the serial input of register B, and both their clocks are connected to an AND gate, which the input of the AND gate is connected, one of them to the clock, the other one to the shift control. Now let's see how this works. Obviously, we don't have any control on the clock. We have a certain frequency. The clock is oscillating. The signal on the clock is oscillating. And we have the shift control. As soon as the shift control is 1, that multiplies to the clock. And when the clock is 1 and the shift control is 1, the AND gate output would be 1. So at this point, shift, let me do it with a different color. At this point, the shift control is 1 and the clock is also 1. Therefore, the shift register T1 will go to 1. And then when, I'm sorry, the clock CLK, the clock of the shift register, which is this clock, will go to 1 and then 0 and then 1. So it's going to just follow the original clock as long as the shift control is 1. When the shift control becomes 0, after that, again, the clock is completely 0. Now, suppose we have two 4-bit shift registers. And this table shows the values of them. We have the timing pulse on the left column, which shows the initial value after T1, after T2, after T3, and after T4. By the way, these T's are the clocks that are connected to the registers. And imagine if shift register A is 1, 0, 1, 1, and shift register B is 0, 0, 1, 0. What happens in shift register 1 or A? Again, this is a shift to right system. So if it's 1, 0, 1, 1, if I shift 1 bit to the right, this 1 falls out and goes back. So this becomes 1, 1, 0, 1. Okay. What happens to shift register B? Imagine if initially shift register B is 0, 0, 1, 0. Shift register B is an open loop system. If I shift everything to the right, what happens to this? Everything will be shifted 1 to the right. And this 0 would fall out. And I would have an empty space here on the left. Where do I fill this empty space? I fill it with the 1 that I had here because this is connected here. Okay, so the answer for the second one would be, this would be 1, 1, 0, 1, and this would be 1, 0, 0, 1. Now let's shift it one more time. So this is 1, 0, 1, 1, 0, 1. If I shift it one more time to the right, what do I have?
0, 1.
No, I'm shifting it, and at the same time, this is coming back. It's a looped system. So if everything shifts to the right, I would have, and this one goes back here, I would have 1, 1, 1, 0. Am I correct? What about this one? This one was 1, 0, 0, 1. If I shift everything to the right, this one would fall off, and I'm having 0 coming in from the other one. So it's going to be 0. This one would be 0, 1, 0, 0. I'm sorry, I had the 1 from the previous one. So it's going to be 1, 1, 0, 0. Yeah, because this one, actually, this one that we shifted to the left is coming to this, to the first bit on the left. Now, the one that we got here, we started with 1, 0, 1, 1, then was 1, 1, 0, 0, then it was 1, 1, 1, 0. So 1, 0, 1, 1, then 1, 1, 0, 1, and then 1, 1, 1, 0. And for register B, it was 0, 0, 1, 0, then 1, 1, 1, 0, 0, 1, and then 1, 1, 0, 0. Now, if I shift this one more time to the right, this is what's going to happen. This 1 goes back here, so it's going to be 0, 1, 1, 1, 1. So 0, 1, 1, 1, 1. What happens to the register B? Everything shifts to the right. This 0 falls off, and this 0 that we had here goes there as well. So it's going to be 0, 1, 1, 0. 0, 1, 1, 0. Is it clear? Now this one, if I shift everything to the right, this one would come here. So next one would be 1, 0, 1, 1. And this 0 would fall out, and we would have a 1 coming to the left. So it's going to be 1, 0, 1, 1. Is it clear, or am I making it very? Okay. So this is how a serial mode would work. Now we can use this for what we call a serial addition. In digital computers, operations are usually executed in parallel since it's faster. Serial mode is sometimes preferred since it requires less equipment. This is an example of using 2 registers, shift register A and B, and a full adder, plus a D flip-flop to create a serial addition system. Let's see how many of these. Now, how does this serial addition system work? It has been explained here. We have A and B, which are 2-bit shift registers. We have the reset, the clock, the shift control, shift register A, shift register B, serial input, and C input. Now, one thing to keep in mind, when we press reset to 0, everything becomes 0. So at this point, everything becomes 0. So we will start from 0, 0, or 1, 1. Now, we have clock here, but since the shift control is 0, none of the shift registers would change. It's locked. Until here that the load becomes 1, but again, nothing would happen because I don't have a clock. So everything starts at this point when I both have a clock and I have a load of 1, a shift control of 1. So the clock is, again, rising edge triggered, and then we have the shift control 1. And what happens here? It changes the status of shift register A, and it changes when we change shift register A, it would also change shift register B. And since the serial input here was 1, what happens, it will add to shift register B, for example, because we have, again, a serial input. Why is it added to shift register B? Because here our serial input is connected to shift register B. It's not connected to shift register. Nothing is connected to shift register. Therefore, shift register B goes from 0, 0 to 1, 0. And then shift register B is connected, the serial output is connected to B, to the full adder, and then the sum is connected to shift register A, and then the carry is connected back. So 0, 0 plus 0, 1 gives us 0, 1. So we're going to have 0, 1 in the output. Again, we have nothing added to that here, but now serial A is 1, 0. And if I add 1, 0 to 1, 0, then I will have 0, 1 in one register and 0, 1 to the other. And 0, 1 plus 0, 1 would give us, again, 1, 1. And then 1, 1 would set back to 0, 0. So what happens is just adding 1. It goes from 0, 0, 0, 0 to 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. And there is a table for this that I will show you what happens. And again, all of this relates to the serial input. Here, the serial input is 1, then it becomes 0, then 1 and 0. That's the reason we have the changes in going from 0, 1 to 1, 0 to 1 to 0, 1 to 0, 0, and so on. And this gives us the carry, which, again, if I add these two together, I would have a carry on of 1. Now, for designing a serial adder, we have the present state, which is Q. Inputs are X and Y. In the next state is Q. The output is S, and the flip-flop inputs, which is a JK flip-flop, 0, X. And you can see here, using this system, we can design it with a JK flip-flop. And here, JQ would be XY, KQ would be X prime, Y prime, and S would be X, XOR with Y, XOR with Q. Now, using this system, instead of having this table, instead of having the full adder, we can use a JK flip-flop and do the same thing. So what technically this did is we got the outputs from the previous circuit when we solved it, and we will replace it with a JK flip-flop. And we can design it using a JK flip-flop instead of having the full adder and also having the D flip-flop that we had. So D flip-flop and the full adder are replaced with this JK flip-flop. I think it's enough for today up to here, because after this point we have universal shift registers, and I don't think I have time to finish it. But yeah, I think at this point, up to this point, is enough. And we will continue this on Thursday. We're going to go to the lab. This week, we're going to do the 2 to 4 decoder. And you're going to build one using a NOT gate and 4 AND gates. the reason I'm ending the class a little sooner because we need time to build this circuit. Thank you so much, and I will see you on Thursday.